In 1981, astronomer Robert Kirshner was mapping the universe when his computer revealed something impossible. Where 700 billion galaxies should exist, he found almost nothing. A spherical region of space so vast it could swallow our entire local group of galaxies billions of times over. Yet it contains only 60 lonely galaxies drifting through an ocean of darkness. This is the Boötes Void, the largest known hole in the universe, stretching 330 million light-years across. If you enjoy discovering the most extreme places in our cosmos, hit that like button because we're about to explore regions where the very fabric of space-time behaves differently. Prepare yourselves. We begin. Picture the largest census ever attempted in human history, counting every single person on Earth, every animal, every tree. Now imagine doing this for the entire universe. That was exactly what astronomers were trying to do in the late 1970s. They pointed their telescopes at patch after patch of sky, measuring the light from distant galaxies. Each galaxy was like a distant city, glowing with the combined light of billions of stars. The goal was simple: create the first three-dimensional map of our cosmic neighborhood. Map every galaxy within a billion light-years of Earth. But as the data poured in, something disturbing began to emerge. In certain regions of space, their instruments detected galaxy after galaxy, clustering together in vast chains and sheets. These cosmic cities were everywhere, exactly as expected. The universe seemed crowded with them. Then they turned their attention to a region in the direction of the constellation Boötes. The constellation itself blazed with familiar stars, including the bright orange giant Arcturus, one of the brightest stars in our night sky. Behind this stellar backdrop, they expected to find the usual cosmic metropolis, packed with thousands of galaxies. Instead, their instruments found almost nothing. At first, the astronomers assumed their equipment had malfunctioned. Perhaps dust clouds were blocking their view, or maybe their telescopes needed recalibration. They checked and double-checked their instruments. Everything worked perfectly. They tried again, scanning deeper into space, looking for the faint glimmer of distant galaxies. Still nothing. Where they should have detected roughly 2,000 galaxies in a region this size, they found fewer than 60. It was like discovering that an entire continent had no cities, no towns, no villages, just empty wilderness stretching for thousands of miles. The mathematical probability of such emptiness occurring by random chance was virtually zero. In a universe that seemed fairly uniform everywhere else, this region defied explanation. It was as if someone had scooped out a massive chunk of the cosmos, leaving behind only darkness. The few galaxies they did detect floated in isolation, separated by distances so vast that if you lived on a planet in one of these lonely galaxies, you might never know other galaxies existed. Your entire observable universe would be almost completely dark, filled with nothing but the scattered light of your own galaxy's stars. As more data confirmed this impossible discovery, astronomers realized they had found something that challenged everything they thought they knew about how the universe was built. This was not just empty space. This was something far stranger, a supervoid so large it seemed to violate the very principles of cosmic structure formation. What could possibly create such a colossal hole in the fabric of space itself? Robert Kirshner stared at his computer terminal in disbelief, watching numbers scroll across the green phosphor screen that would change astronomy forever. The Harvard-Smithsonian astronomer had spent months collecting galaxy redshifts, measurements that revealed how fast distant galaxies were moving away from Earth due to cosmic expansion. By measuring these redshifts, he could calculate exact distances to galaxies, creating the first detailed three-dimensional maps of our cosmic neighborhood. His team had divided the sky into sections, methodically scanning each region with the precision of cartographers mapping uncharted territories. They used a technique called pencil beam surveying, pointing their telescopes at narrow strips of sky and measuring every galaxy they could detect. When Kirshner analyzed 3 separate fields, each separated by 35 degrees, he expected to see the normal distribution of galaxies at various distances. Instead, all three regions showed an identical and disturbing pattern, a complete gap in the redshift distribution at 15,000 kilometers per second. This gap represented a specific distance from Earth, roughly 700 million light-years away. At that distance, in all three directions, galaxies simply vanished. The probability of this happening by chance was less than finding the same lottery number drawn 3 times in a row. Kirshner convinced his colleagues, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, to join a follow-up survey. Together, they measured the redshifts of 240 bright galaxies in the region between their original 3 fields. The results were even more shocking. Not a single galaxy existed in the redshift range between 12,000 and 19,000 kilometers per second. Based on the average density of galaxies throughout the universe, they should have found 31 galaxies in this range. Instead, they found 0. The team had discovered what would become known as the Boötes Void, named after the constellation where it appeared to be located. Their measurements revealed a roughly spherical region of space, 330 million light-years in diameter, that contained virtually no galaxies. To put this in perspective, imagine if you tried to find cities while flying across the United States, but instead of discovering New York, Chicago, and Los Angeles, you found only empty prairie stretching from coast to coast. The Boötes Void was proportionally even emptier than that. The discovery sent shockwaves through the astronomical community. Scientists had theorized that the universe might contain small empty regions, but nothing approaching this scale. The Boötes Void was larger than anything predicted by models of cosmic structure formation. Kirshner and his team published their findings, but many astronomers initially remained skeptical. How could such an enormous void exist without violating our understanding of how the universe evolved? Some suggested it might be an observational error, or perhaps a region obscured by dust. However, subsequent surveys confirmed the void's existence and revealed its true nature. This was not an error or an illusion. This was a genuine hole in the universe, so vast it challenged the fundamental assumptions about cosmic evolution. The question now became, if voids this large could exist, what did it mean for our understanding of the universe itself? To truly grasp the monstrous scale of the Boötes Void, we need to shrink the universe down to something our minds can actually process. Imagine our Milky Way galaxy as a single grain of sand on a beach. This grain contains 400 billion stars, including our Sun, plus all the planets, asteroids, and cosmic debris within a region spanning 100,000 light-years. Every star you see in the night sky, every constellation, every nebula, photographed by the Hubble Space Telescope, all of it fits within this single grain of sand. Now, if the Milky Way is one grain of sand, our local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, would be roughly the size of a marble. This marble represents a region 10 million light-years across, containing trillions of stars and countless planets. The Boötes Void, on this same scale, would be a hollow sphere the size of a basketball court. Inside this enormous space, you would find fewer than 60 grains of sand, scattered randomly with vast distances between them. The rest would be completely empty. But let us return to real cosmic dimensions to truly appreciate this monster. The Boötes Void stretches 330 million light-years from one edge to the other. Light, traveling at 186,000 miles per second, would take 330 million years to cross from one side to the other. If you could somehow travel at the speed of our fastest spacecraft, New Horizons, which reached speeds of 36,000 miles per hour on its way to Pluto, crossing the Boötes Void would take you roughly 2 trillion years. That is 150 times longer than the current age of the universe. The void contains a volume of roughly 36 million cubic megaparsecs. To put this in perspective, if you filled this volume with Earth-sized planets, you could fit 10 to the power of 39 planets inside it. That number has 39 zeros after it, more planets than there are atoms in a human body. Within this incomprehensible volume of space, astronomers have detected only about 60 galaxies. In a typical region of the universe this size, we would expect to find approximately 2,000 galaxies. The void is roughly 30 times emptier than average cosmic space. These 60 lonely galaxies drift through the darkness like isolated islands in a cosmic ocean. The nearest neighbors to any galaxy in the void are separated by distances of 50 to 100 million light years. For comparison, our nearest major galactic neighbor, Andromeda, is only 2.5 million light years away. If Earth existed in a galaxy within the Boötes Void, our night sky would be profoundly different. Instead of seeing thousands of stars and the faint glow of distant galaxies, we would see only the stars of our own galaxy against a backdrop of almost perfect darkness. The universe would appear smaller, lonelier, and far more mysterious. The sheer scale of this emptiness forces us to confront an uncomfortable truth. Our universe is far stranger and more extreme than we ever imagined. The numbers behind the Boötes Void reveal something so statistically impossible that it challenges our understanding of probability itself. Start with this. Astronomers calculate the average density of matter in the universe at roughly 1 proton per cubic meter. That might sound empty, but distributed across cosmic scales, this tiny amount of matter creates the galaxies, stars, and planets we observe everywhere. In a typical region of space, the size of the Boötes Void, statistical models predict we should find approximately 2,000 galaxies. These models are based on decades of observations from millions of galaxies across the observable universe. They work reliably in virtually every other region of space astronomers have surveyed. Yet the Boötes Void contains only 60 galaxies. That represents a density roughly 30 times lower than the cosmic average. The mathematical probability of such a deviation occurring randomly is approximately 1 in 10 million. To put this in perspective, you are more likely to be struck by lightning twice in the same day than to find a void this empty by pure chance. But the statistical impossibility becomes even more disturbing when we consider the void's spherical shape. Random fluctuations in galaxy distribution should create irregular, chaotic patterns. The Boötes Void, however, forms an almost perfect sphere, with galaxies clustered primarily in a tube-shaped region running through its center. The spherical symmetry suggests that some fundamental process shaped this region, rather than random statistical fluctuations. This is like flipping a coin 1,000 times and getting heads exactly 500 times, then tails exactly 500 times, in perfect alternating order. The void's size creates additional mathematical challenges. According to standard models of cosmic structure formation, voids this large should not exist. The gravitational forces that shape the universe over billions of years should prevent such extreme underdensity on scales larger than about 100 million light years. Computer simulations of cosmic evolution, running on the world's most powerful supercomputers, struggle to reproduce voids approaching the Boötes Void's dimensions. These simulations model the growth of structure from tiny quantum fluctuations in the early universe to the present day. They successfully predict the formation of galaxy clusters, filaments, and smaller voids. But supervoids, like Boötes, remain outliers. The energy required to evacuate this much space through gravitational processes is staggering. Imagine trying to remove all the air from a sphere 1,000 miles in diameter using only vacuum pumps. The Boötes Void represents a similar feat on cosmic scales, but instead of air, we are talking about removing most of the dark matter and normal matter from a region larger than most galaxy superclusters. Some astronomers have calculated that creating such a void would require the equivalent energy of exploding 10 to the power of 60 hydrogen bombs simultaneously. This number is so large that writing it out would require more digits than there are atoms in a mountain. The mathematical impossibility of the Boötes Void suggests that our models of cosmic evolution are incomplete. Something in the early universe, some process we do not yet understand, carved out this enormous hollow in the fabric of space itself. What force could be powerful enough to create such mathematical impossibility 13.8 billion years ago, in the first trillionth of a trillionth of a trillionth of a second after the Big Bang? The universe underwent the most violent expansion in cosmic history. During this period, called cosmic inflation, space itself expanded faster than light. Regions that started smaller than a proton were stretched to the size of basketballs in less time than it takes light to travel across an atomic nucleus. This expansion was so rapid and extreme that it amplified tiny quantum fluctuations into cosmic-sized variations in density. Think of inflating a balloon with a slightly wrinkled surface. As the balloon expands, the tiny wrinkles become large hills and valleys. Similarly, microscopic quantum variations in the primordial universe became the seeds for all future cosmic structure. These quantum fluctuations were not random noise. They followed specific mathematical patterns, creating a cosmic web of slightly denser and slightly less dense regions throughout space. The denser regions would eventually become galaxies and galaxy clusters. The less dense regions would become voids. But here is where the story becomes truly fascinating. The pattern of these fluctuations resembled bubbles in foam. Imagine soap bubbles clustering together, with thin films separating hollow interiors. The early universe developed a similar structure, with matter concentrated in bubble walls and vast empty spaces inside the bubbles. As gravity began to dominate cosmic evolution, this bubble-like pattern amplified over billions of years. Matter in the slightly denser regions attracted more matter, growing into the filaments and clusters we observe today. Meanwhile, the underdense regions became increasingly empty as matter was gravitationally pulled toward denser areas. The Boötes Void represents one of these primordial bubbles, grown to enormous proportions over cosmic time. What started as a tiny quantum fluctuation smaller than an electron became a region of space large enough to contain thousands of galaxies, yet containing almost none. Recent computer simulations of cosmic inflation have recreated these bubble-like patterns. When scientists run their models forward in time, they successfully produce cosmic structures remarkably similar to what we observe, including large voids. However, the simulations still struggle to explain voids as large and empty as Boötes. The quantum nature of these fluctuations means that they followed the strange rules of quantum mechanics. In quantum physics, particles can exist in multiple states simultaneously until observed or measured. Some theoretical physicists suggest that cosmic voids might represent regions where quantum superposition operated on cosmic scales during inflation. This possibility leads to mind-bending implications. The Boötes Void might be a fossil remnant of quantum processes that operated when the universe was smaller than an atom. In effect, we are observing the macroscopic consequences of microscopic quantum events that occurred before matter, energy, space, and time had settled into their familiar forms. The cosmic microwave background radiation, the afterglow of the Big Bang, preserves a snapshot of these primordial fluctuations. Astronomers can measure tiny temperature variations in this ancient light and compare them to the current distribution of galaxies and voids. These comparisons reveal that cosmic voids like Boötes formed from some of the earliest and most fundamental processes in cosmic history, written in the quantum foam that preceded everything we know. Dark matter, the invisible substance that comprises 27% of the universe, flows through space like a vast cosmic river system, and the Boötes Void sits at the center of the largest drainage basin in the observable universe. Unlike ordinary matter, dark matter interacts only through gravity. It does not emit, absorb, or reflect light, making it completely invisible to telescopes. We detect its presence only through its gravitational effects on visible matter and the bending of light from distant galaxies. Computer simulations reveal that dark matter forms the scaffolding upon which all cosmic structure builds. Picture dark matter as an invisible highway system connecting major cities. Galaxies form where these highways intersect, while voids exist in the vast empty regions between highway networks. The Boötes Void occupies a region where dark matter highways curve around it rather than through it. Like water flowing around a large boulder in a stream, dark matter particles follow paths of least resistance, guided by gravitational forces established during the early universe. This creates a feedback effect that grows more extreme over cosmic time. As dark matter avoids the void region, it carries ordinary matter with it gravitationally. Gas clouds, dust, and the raw materials for star formation all get swept along these dark matter currents, leaving the void increasingly empty. The boundaries of the Boötes Void mark the locations where these dark matter highways converge into superclusters. The Hercules supercluster, containing thousands of galaxies, lies along one edge of the void. The Corona Borealis supercluster sits on another edge. These massive structures act like cosmic dams, collecting matter that flows around the empty region. Gravitational mapping, using weak lensing techniques, allows astronomers to trace these invisible dark matter highways. When light from distant galaxies passes through regions containing dark matter, the gravitational field slightly bends the light, creating measurable distortions in galaxy shapes. These measurements reveal that dark matter density drops to roughly 15% of the cosmic average within the Boötes Void. While this might not sound extremely empty, remember that dark matter is normally invisible. For its density to drop this low suggests that even this invisible component actively avoids the void region. The motion of dark matter particles also differs dramatically within voids compared to dense regions. In galaxy clusters, dark matter particles orbit in complex patterns, bound by strong gravitational fields. Within the Boötes Void, dark matter particles move in nearly straight lines across vast distances, experiencing minimal gravitational influence. This creates what physicists call a slow motion zone, where cosmic evolution proceeds differently. Galaxy formation becomes extremely difficult because there is insufficient dark matter to provide gravitational seeds around which ordinary matter can condense. Some theoretical models suggest that the few galaxies within the Boötes Void formed through different mechanisms than galaxies elsewhere in the universe. Instead of condensing around dark matter concentrations, they might represent rare instances where ordinary matter overcame the lack of dark matter, scaffolding through pure chance or unusual initial conditions. The dark matter highways surrounding the void continue to drain it of remaining matter, making it increasingly empty over cosmic time. Eventually, these regions will become the loneliest places in the universe. In the vast darkness of the Boötes Void, 60 galaxies drift in isolation so profound that if intelligent life existed within them, they might never discover the rest of the universe exists. Each of these cosmic islands represents a collection of hundreds of billions of stars, yet they are separated by distances that dwarf anything in our local cosmic neighborhood. The average separation between void galaxies is roughly 100 million light-years, compared to the 2.5 million light-years separating our Milky Way from Andromeda. To put this isolation in perspective, imagine standing in the center of Texas and knowing that the nearest other person lives somewhere in Alaska, but you do not know exactly where. That represents the loneliness these galaxies experience, except multiplied across cosmic distances that make interplanetary travel seem trivial. The most detailed studies of void galaxies reveal that they differ fundamentally from galaxies in denser regions of the universe. They tend to be smaller, containing fewer stars, and show less evidence of the violent merger events that shape galaxies elsewhere. It is as if they evolved in cosmic isolation, undisturbed by the gravitational chaos that characterizes most of the universe. One of the most prominent void galaxies, designated Markarian 845, shines at 14th magnitude, making it barely visible to large amateur telescopes despite being a substantial galaxy containing billions of stars. If this same galaxy existed in a dense region of space, it would appear much brighter due to gravitational interactions with neighboring galaxies that trigger bursts of star formation. The spectral signatures of void galaxies show they contain older stellar populations, on average, with less active star formation than their counterparts in dense cosmic regions. This suggests they exhausted their raw materials for making new stars early in their evolution and have been slowly fading ever since. Perhaps most remarkably, these galaxies arrange themselves in a peculiar pattern within the void. Rather than being randomly distributed, most of the 60 galaxies lie along a tube-shaped structure running through the center of the void. This tube is roughly 50 million light-years wide and stretches across the entire void diameter. The tube structure suggests that, even within the void, matter followed specific gravitational channels during the early universe. It is like finding that 60 cities in an otherwise empty continent all happen to be built along a single transcontinental highway. From the perspective of a hypothetical observer on a planet within one of these void galaxies, the night sky would appear profoundly different from ours. Instead of seeing the faint glow of distant galaxies and star clusters, they would observe mostly darkness, punctuated only by the stars of their own galaxy. Such an observer might conclude they lived in a much smaller, lonelier universe. They would have no way to detect the cosmic microwave background radiation easily, no obvious evidence for the Big Bang, and no clear indication that billions of other galaxies existed beyond their cosmic horizon. Some astronomers have calculated that if Earth existed in one of these void galaxies, we would not have discovered the expansion of the universe until the 1960s, when telescope technology finally became sensitive enough to detect the few neighboring void galaxies. These 60 galaxies represent cosmic hermits, evolutionary, isolated from the rich interactions that shape most galactic evolution across the universe. The universe resembles a vast three-dimensional spiderweb, with galaxies strung along thin filaments separated by enormous empty spaces, and the Boötes Void represents one of the largest holes in this cosmic web. This web-like structure emerged from the distribution of matter in the early universe. Computer simulations show that as gravity amplified tiny initial density variations over billions of years, matter naturally organized itself into sheets, filaments, and nodes, while evacuating the spaces between them. Picture soap suds in a bathtub. The soap forms thin films that intersect at edges and corners, while most of the volume consists of empty bubbles. The cosmic web follows a similar pattern, with most galaxies concentrated in the soap film-like structures, while vast bubble-like voids occupy most of the volume. Measurements from large galaxy surveys reveal that roughly 80% of the universe's volume consists of voids like Boötes, while only 20% contains the filaments and clusters where most galaxies reside. This means emptiness, not matter, dominates the large-scale structure of our cosmos. The filaments themselves are remarkably thin, considering their enormous length. A typical filament might stretch hundreds of millions of light-years, while being only 10 to 20 million light-years thick. These cosmic highways channel matter, flow across vast distances, connecting galaxy clusters and feeding their growth over cosmic time. Where filaments intersect, they create nodes that become the sites of massive galaxy clusters containing thousands of individual galaxies. These clusters represent some of the most massive gravitationally bound structures in the universe, with masses equivalent to millions of billions of suns. The Boötes Void sits in a region where the cosmic web's filaments curve around it rather than through it. Like a bubble in foam, The void is bounded by several major filaments containing galaxy superclusters. The Hercules supercluster, Corona Borealis supercluster, and other massive structures form the void's boundaries. This web-like arrangement explains why voids can become so empty over cosmic time. Matter naturally flows along the filaments toward nodes and clusters, abandoning the interior regions of voids. The gravitational attraction of surrounding dense regions acts like a cosmic drainage system, pulling matter out of voids and concentrating it in filaments. The cosmic web also influences how galaxies evolve. Galaxies in dense filaments and clusters experience frequent gravitational interactions, mergers, and encounters that trigger star formation and shape their morphologies. Galaxies in voids, isolated from these interactions, evolve more slowly and retain their primordial characteristics longer. Recent observations using gravitational lensing have directly detected some of the dark matter filaments predicted by cosmic web models. These invisible highways of dark matter guide the flow of ordinary matter and help maintain the web's structure over cosmic time. The web continues to evolve as cosmic expansion accelerates due to dark energy. Future observations suggest that voids will grow larger while filaments become thinner, making the cosmic web more extreme over time. Understanding this web-like structure helps explain why regions like the Boötes Void can exist and why they represent a fundamental feature of cosmic architecture rather than unusual anomalies. The cosmic web reveals that emptiness and structure exist in a delicate cosmic balance, with each defining the other. The existence of the Boötes Void shatters fundamental assumptions about how galaxies form and challenges models that have guided astronomy for decades. According to standard theories of cosmic evolution, galaxies form when dark matter halos reach sufficient mass to begin attracting and condensing ordinary matter. These halos grow through mergers and accretion, eventually becoming massive enough to trigger star formation and create the galaxies we observe. The problem is that this process should not leave regions as empty as the Boötes Void. Even if an area started with below-average matter density, the gravitational collapse of surrounding regions should not evacuate it so thoroughly. Computer simulations consistently predict that voids this large and empty should not exist. Most models of structure formation, based on cold dark matter cosmology, predict maximum void sizes of roughly 150 million light-years in diameter. The Boötes Void, at 330 million light-years across, exceeds these predictions by more than a factor of 2. Even more troubling, the void's extreme emptiness contradicts predictions about how cosmic expansion should work. As the universe expands, even underdense regions should retain roughly 15 to 20% of the cosmic average matter density. The Boötes Void falls well below this minimum, suggesting that some additional physical process must be removing matter from these regions. The few galaxies within the void present their own puzzles for galaxy formation theory. These galaxies show different properties from their counterparts in dense cosmic regions. They tend to be smaller, contain older stellar populations, and show less evidence of recent star formation or mergers. Traditional galaxy formation models predict that isolated galaxies should actually be larger and more massive, not smaller. Without gravitational harassment from neighboring galaxies, void galaxies should retain more of their initial gas supplies and continue forming stars at higher rates for longer periods. Instead, void galaxies appear to have shut down their star formation earlier than expected, as if they ran out of raw materials despite their isolation. This suggests that the void environment itself somehow inhibits galaxy growth through mechanisms not included in current theoretical models. The distribution of the 60 void galaxies along a tube-like structure also defies standard predictions. Random cosmic processes should distribute galaxies more uniformly throughout the void volume. The observed concentration along a central filament implies that some organizing principle guided their formation and evolution. Some astronomers have proposed exotic explanations for these discrepancies, perhaps primordial black holes or other unusual forms of matter created the void through processes we do not understand. Others suggest that modifications to general relativity or dark matter properties might explain the void's extreme characteristics. Alternative theories of cosmic evolution, such as those involving variable dark energy or modified gravity, can better accommodate supervoids like Boötes. However, these theories often make other predictions that conflict with astronomical observations, creating new problems while solving old ones. The most honest assessment is that the Boötes Void reveals gaps in our understanding of fundamental cosmic processes. Despite decades of increasingly sophisticated observations and theoretical modeling, we cannot fully explain how such extreme structures form and evolve. This void forces astronomers to confront the possibility that our models of cosmic evolution are incomplete and that the universe contains physical processes we have yet to discover. The cosmic microwave background radiation, the afterglow of the Big Bang, carries the fingerprints of cosmic voids imprinted 13.8 billion years ago, and these fingerprints reveal how structures like the Boötes Void shaped the very fabric of space-time. This ancient light, cooled by cosmic expansion to just 2.7 degrees above absolute zero, shows tiny temperature fluctuations that correspond to density variations in the early universe. Regions that would become voids appear as slightly warmer spots, while areas destined to become galaxy clusters show up as cooler regions. The connection between voids and these temperature patterns involves a phenomenon called the integrated Sachs-Wolf effect. As ancient light traveled through regions of changing gravitational potential over billions of years, it gained or lost energy depending on whether the gravitational field was growing stronger or weaker. Light passing through regions that became voids experienced decreasing gravitational fields as matter evacuated these areas. This caused the light to lose energy and appear cooler when it finally reached Earth. Conversely, light traveling through increasingly dense regions gained energy and appears warmer in the cosmic microwave background. Large voids like Boötes create detectable cold spots in this ancient radiation. The European Space Agency's Planck satellite has mapped these temperature variations with extraordinary precision, revealing correlations between the largest cosmic voids and specific cold regions in the microwave background. One particularly intriguing cold spot, located in the direction of the constellation Eridanus, may be associated with an even larger supervoid than Boötes. This cold spot appears roughly 5 times larger than typical temperature fluctuations and has puzzled astronomers since its discovery by the Wilkinson Microwave Anisotropy Probe. The temperature difference between void-associated cold spots and the average background radiation amounts to only a few millionths of a degree. Despite being almost unimaginably small, these variations provide crucial evidence about how cosmic structures evolved over billions of years. Advanced computer simulations can now trace the evolution of individual regions from the patterns visible in the cosmic microwave background to their current states. These simulations confirm that areas showing particular temperature signatures in the ancient radiation did indeed become large voids like Boötes. However, the simulations also reveal a troubling discrepancy. The observed cold spots associated with supervoids appear larger and more pronounced than theoretical models predict. This suggests that either our understanding of void evolution is incomplete, or that exotic physics beyond the standard model influenced their development. Some theoretical physicists have proposed that the cold spots might result from cosmic strings, topological defects in space-time, left over from the very early universe. Others suggest they could be signatures of collisions between our universe and parallel universes during cosmic inflation. More conventional explanations focus on the possibility that dark energy behaves differently within voids than in dense regions. If dark energy has unusual properties on large scales, it could enhance the growth of voids and create stronger signatures in the microwave background than standard models predict. The study of void-associated cold spots represents one of the most active areas of current cosmological research. Future missions and ground-based experiments will map these temperature patterns with even greater precision, potentially revealing new physics hidden in the cosmic void. These ancient light patterns prove that cosmic voids like Boötes are not recent developments, but fundamental features of cosmic architecture established during the universe's infancy. Trillions of neutrinos, the universe's most elusive particles, flood through the Boötes Void every second, creating a cosmic laboratory for studying these ghostly messengers from the Big Bang. Neutrinos are among the strangest particles in physics. They have almost no mass, no electric charge, and interact so weakly with matter that they can pass through entire planets without touching a single atom. Every second, roughly 100 billion neutrinos pass through each square inch of your body without you feeling anything. These particles were created in enormous quantities during the Big Bang and continue streaming through space, essentially unaffected by the evolution of cosmic structure. Unlike photons, which interact with matter and lose energy over cosmic time, neutrinos maintain their primordial properties and carry information about conditions in the very early universe. The Boötes Void provides an almost perfect laboratory for studying these primordial neutrinos because there is so little matter to interfere with their free passage. In dense regions of the universe, neutrinos can occasionally interact with atomic nuclei or be deflected by gravitational fields. Within the void, they travel in nearly perfect straight lines across hundreds of millions of light years. This creates opportunities to study neutrino properties that are impossible elsewhere in the universe. The European Space Agency's Euclid mission, designed to map cosmic structure with unprecedented precision, will use voids like Boötes to measure the sum of neutrino masses by observing their subtle gravitational effect. Even though individual neutrinos have tiny masses, their collective gravitational influence becomes measurable on cosmic scales. In regions where matter density is extremely low, such as supervoids, the gravitational effects of neutrino background become relatively more important and potentially detectable. Neutrinos also provide a way to test fundamental physics across cosmic distances. If certain theoretical predictions about neutrino properties are correct, their behavior within voids might reveal violations of basic symmetries or evidence for new physical forces. The streaming motion of neutrinos through voids affects the evolution of cosmic structure in subtle but measurable ways. Computer simulations that include neutrino physics predict slightly different void properties than simulations that ignore these particles. Comparing observations of supervoids like Boötes with these theoretical predictions helps constrain neutrino masses and properties. Some of the most energetic neutrinos in the universe are produced by extreme astrophysical events, such as supernovae, gamma-ray bursts, and active galactic nuclei. These high-energy neutrinos can travel billions of light years through space, and voids provide clear paths for them to reach Earth without being absorbed or scattered. The IceCube Neutrino Observatory, buried beneath the Antarctic ice, has detected neutrinos that traveled through cosmic voids on their way to Earth. By studying the arrival directions and energies of these particles, astronomers can map the invisible neutrino universe and identify which cosmic events produced them. Future neutrino telescopes will use cosmic voids as natural beamlines, studying how neutrinos behave over the largest possible distances. These experiments might discover whether neutrinos have exotic properties, such as the ability to oscillate into sterile neutrino states or interact with dark matter particles. The Boötes Void, empty of almost everything else, becomes filled with information carried by these invisible messengers from the cosmic dawn. Within the Boötes Void, the mysterious force driving cosmic acceleration operates with almost no opposition, creating a region where dark energy dominates more completely than anywhere else in the universe. Dark energy, comprising roughly 68% of the universe's total energy density, acts like anti-gravity on cosmic scales. While gravity pulls matter together, dark energy pushes space itself apart, causing the accelerating expansion discovered in 1998 through observations of distant supernovae. In dense regions of the universe, gravity and dark energy engage in cosmic tug-of-war. Galaxy clusters and superclusters grow larger as gravity overcomes dark energy on local scales, while the overall expansion accelerates due to dark energy's dominance on larger scales. But within supervoids like Boötes, there is insufficient matter to provide significant gravitational resistance to dark energy's push. The result is that these regions expand faster than the cosmic average, becoming increasingly empty over time. Computer simulations reveal that voids act as cosmic accelerators, expanding at rates up to 30% faster than the overall universe. This enhanced expansion rate helps explain why voids become so extremely underdense compared to theoretical predictions based on initial conditions. The accelerated expansion within voids creates a feedback effect. As the void expands faster, its density drops further below the cosmic average, reducing gravitational attraction from within and allowing dark energy to dominate even more completely. This process continues until the void becomes a region where dark energy controls cosmic evolution almost unopposed. Some theoretical models predict that dark energy itself might behave differently within voids compared to dense regions. If dark energy has properties that depend on local matter density, voids could experience stronger acceleration than current models assume. This possibility has led to proposals for using cosmic voids as laboratories for testing theories of dark energy. Different models of dark energy make subtly different predictions about how voids should evolve over cosmic time. Comparing observations of supervoids like Boötes with these predictions might reveal the true nature of dark energy. The Euclid Space Telescope and other future surveys will measure void expansion rates directly by observing how the boundaries of voids change over cosmic time. These measurements could distinguish between various dark energy models and reveal whether this mysterious force has constant or variable properties. Within the Boötes Void, the few galaxies that do exist show signatures of enhanced cosmic expansion. Their recession velocities follow patterns that differ subtly from galaxies in dense regions, providing additional evidence for accelerated expansion within void interiors. The study of void dynamics also relates to fundamental questions about the nature of space-time itself. Some modified theories of gravity propose alternatives to dark energy that make different predictions about how empty regions should evolve. As dark energy continues driving accelerated expansion, voids like Boötes will become increasingly dominant features of cosmic architecture. In the far future, these regions will grow so large that galaxies within them lose causal contact with the rest of the universe. The Boötes Void represents a preview of our universe's ultimate fate. Vast regions of space where dark energy reigns supreme over increasingly isolated islands of matter. The Boötes Void did not form as a single, massive, empty region, but instead represents the cosmic equivalent of soap bubbles merging together, growing larger through billions of years of gravitational evolution. Computer simulations of cosmic structure formation reveal that the early universe contained numerous small voids, each roughly 10 to 50 million light-years across. These primordial bubbles formed from quantum fluctuations during cosmic inflation, creating a foam-like pattern in the distribution of matter and dark matter. As the universe expanded and evolved, gravity shaped this initial foam structure. Dense regions between bubbles attracted more matter and grew into the filaments and clusters we observe today. Meanwhile, the underdense bubbles began to merge, creating larger and larger empty regions. The process resembles what happens when you blow soap bubbles in a bathtub. Small bubbles naturally combine when they touch, forming progressively larger bubbles. The thin soap films separating bubbles become thinner as bubbles grow, just as the matter between cosmic voids becomes more concentrated in filaments as voids merge. Advanced simulations suggest that the Boötes Void formed from the merger of roughly 6 to 10 smaller voids over a period of several billion years. Each merger event evacuated additional matter from the region, making the combined void increasingly empty. The merger process explains several puzzling features of the Boötes Void. The tube-like structure, containing most of the void's galaxies, likely represents the remnant of boundaries between the original smaller voids. As these voids merged, some matter remained trapped along the merger interfaces, forming the observed galactic filament. Evidence for this merger scenario comes from detailed mapping of galaxy distributions around the void's edges. These maps reveal finger-like extensions and irregularities that match predictions for how multiple smaller voids would combine. The void's nearly spherical shape results from the gravitational smoothing that occurs as merged regions reach equilibrium. The merger process also explains why the Boötes Void appears more empty than theoretical models predict for a single void. Each merger event allowed gravitational attraction from surrounding dense regions to pull additional matter out of the combined void, creating an emptiness that exceeds what any individual void could achieve. Measurements of galaxy recession velocities within and around the void support the merger hypothesis. These velocities show patterns consistent with matter flowing away from multiple centers simultaneously, rather than from a single central point, as would be expected for a primordial void. The timing of void mergers depends critically on the properties of dark energy and the expansion rate of the universe. If cosmic expansion had proceeded differently, the smaller voids might never have had time to merge before being separated by expansion. Future deep galaxy surveys will map void substructure with sufficient detail to identify the boundaries of the original smaller voids that merged to create supervoids like Boötes. This information will provide crucial tests of theories about cosmic structure formation and the role of dark energy in shaping large-scale cosmic architecture. The merger process continues today, though at a much slower rate due to accelerated cosmic expansion driven by dark energy. In regions where voids are still merging, astronomers can observe this process directly and study how the largest structures in the universe continue to evolve. The Boötes Void represents the mature result of this cosmic bubble merging process, a supervoid that consumed its smaller neighbors to become one of the most extreme structures in the observable universe. Within the Boötes Void, time flows at a subtly different rate than in the dense regions of space where we live, creating a cosmic laboratory where Einstein's theories of relativity operate under the most extreme conditions imaginable. According to general relativity, gravitational fields affect the passage of time. Stronger gravity slows time down, while weaker gravity allows time to flow more quickly. This effect, called gravitational time dilation, has been measured everywhere, from Earth's surface to the edge of black holes. In regions of space where matter density approaches the cosmic average, gravitational time dilation remains relatively uniform. Clocks on Earth tick at nearly the same rate as hypothetical clocks placed in typical intergalactic space. The difference amounts to only a few parts per billion over millions of years, but the Boötes Void contains roughly 30 times less matter than average cosmic space. This dramatic reduction in local gravitational field strength means that time flows measurably faster within the void compared to dense regions of the universe. The effect becomes significant when measured over cosmic timescales. A clock placed in the center of the Boötes Void would gain approximately 1 second every million years, compared to a clock located in a typical galaxy cluster. Over the 13.8 billion year history of the universe, this difference accumulates to roughly 14,000 seconds, or nearly 4 hours. This might sound trivial, but the implications are profound for understanding cosmic evolution. Physical processes that depend on precise timing, such as radioactive decay rates and stellar evolution, proceed slightly faster within voids. Stars burn through their nuclear fuel more quickly, supernovae explode earlier, and the entire pace of cosmic evolution accelerates. The time dilation effects also influence how we observe distant galaxies within voids. Light from these galaxies experiences slightly different gravitational conditions during its journey to Earth, causing subtle shifts in spectral features that astronomers must account for when measuring distances and recession velocities. Advanced computer simulations of cosmic evolution now include these relativistic time effects when modeling the formation and growth of large-scale structures. The simulations reveal that voids experience a form of temporal feedback. As they become emptier, time flows faster within them, accelerating the physical processes that make them even emptier. Some theoretical physicists have proposed using cosmic voids as natural laboratories for testing exotic theories of gravity and time. If certain speculative theories are correct, the time dilation effects within supervoids might deviate from Einstein's predictions in measurable ways. The European Space Agency's upcoming atomic clock experiments in space will attempt to measure these cosmic time dilation effects directly. By comparing extremely precise atomic clocks placed at different distances from massive structures, scientists hope to detect the subtle ways that cosmic matter distribution influences the flow of time. The time effects become even more extreme in the hypothetical centers of the largest voids. In these regions, where matter density drops to its absolute minimum, time would flow at its fastest possible rate given the current cosmic matter distribution. This creates the bizarre possibility that advanced civilizations might use voids as cosmic time machines, not for traveling to the past or future, but for experiencing time at different rates compared to the rest of the universe. But even stranger possibilities emerge when we consider that we ourselves might be living inside such a temporal anomaly. Recent astronomical discoveries suggest that our own Milky Way galaxy, along with thousands of neighboring galaxies, sits inside a massive cosmic void that dwarfs even the Boötes Void, fundamentally altering our understanding of our place in the universe. The local hole, also known as the KBC Void, stretches approximately 2 billion light-years across and contains our local group of galaxies, the Virgo supercluster, and numerous other galactic structures we consider part of our cosmic neighborhood. If confirmed, this void would be roughly 6 times larger than the Boötes Void. This discovery emerged from careful measurements of cosmic expansion rates in different directions from Earth. Astronomers expected to find uniform expansion in all directions, consistent with the overall Hubble expansion of the universe. Instead, they detected systematic differences, suggesting that our local region of space is expanding faster than the cosmic average. The evidence comes from observations of Type Is supernovae, stellar explosions that serve as cosmic distance markers. Supernovae, in certain directions, appear slightly brighter than expected, indicating they are closer than standard cosmological models predict. This brightness pattern matches what astronomers would expect if we were located inside a large, underdense region. Additional support comes from measurements of the cosmic microwave background radiation. The motion of our local group relative to this ancient radiation shows patterns consistent with gravitational attraction toward dense structures outside a large local void. If we do live inside such a supervoid, it would explain several puzzling aspects of local cosmic structure. The relatively low density of galaxies in our cosmic neighborhood, the unusual motion of the local group, and discrepancies in measurements of cosmic expansion rates could all result from our void-dwelling perspective. The implications extend far beyond local astronomy. Many fundamental cosmological measurements, including the Hubble constant that describes cosmic expansion rate, depend on observations of relatively nearby objects. If these objects are located within the same void as Earth, our measurements might not represent the true cosmic averages. This possibility has sparked intense debate within the astronomical community. Some studies support the void hypothesis, while others argue that statistical fluctuations or observational biases could explain the unusual measurements without requiring a local supervoid. The controversy relates to broader questions about the nature of cosmic expansion and dark energy. Different models of dark energy make different predictions about how local voids should affect our observations of cosmic acceleration. Computer simulations suggest that an observer inside a large void would perceive cosmic expansion as accelerating even without dark energy due to gravitational effects from surrounding dense regions. This raises uncomfortable questions about whether dark energy discoveries might partly result from our location bias. Future surveys will test the local void hypothesis by mapping galaxy distributions out to distances of several billion light-years. These observations should reveal whether the apparent underdensity around our local group represents a genuine large-scale structure or merely a statistical fluctuation. The Dark Energy Survey, the Euclid mission, and other ambitious projects will provide unprecedented maps of cosmic structure, extending well beyond any hypothetical local void. These surveys will either confirm our special location within a supervoid or demonstrate that cosmic structure appears uniform when viewed from sufficient distance. Living inside a cosmic void would make Earth's location in the universe far more unusual than previously thought, adding another layer to the cosmic coincidences that allow complex life to exist. The question remains, are we cosmic void dwellers looking out at a denser universe, or do we occupy a typical location in a universe filled with structures like the Boötes Void? Hidden within the apparent emptiness of the Boötes Void, invisible magnetic field lines stretch across distances so vast they could connect entire galaxy clusters, revealing that even the most empty regions of space contain organized structures beyond our imagination. These cosmic magnetic fields are roughly 1 million times weaker than Earth's magnetic field, yet they extend across volumes containing billions of solar systems. To detect something so faint requires the most sensitive instruments in astronomy, capable of measuring magnetic effects that would be undetectable using any laboratory equipment. The discovery came through observations of high-energy gamma rays from distant blazars, extremely bright galaxies powered by supermassive black holes. As these gamma rays travel billions of light-years through space, they occasionally interact with magnetic fields and convert into electron-positron pairs. When astronomers analyzed gamma-ray observations from blazars located behind the Boötes Void, they found subtle absorption signatures indicating the presence of magnetic fields within the supposedly empty region. The strength of these fields reached at least 1/10,000,000th of a Gauss, comparable to magnetic fields found in normal intergalactic space. This discovery revolutionized our understanding of cosmic voids. Rather than being completely empty, voids contain a tenuous network of magnetized plasma organized into structures that mirror the cosmic web on enormous scales. The magnetic field lines appear to follow the void's large-scale structure, running along the boundaries between empty regions and connecting the sparse galaxies within void interiors. Like invisible highways, these field lines provide pathways for charged particles to travel across otherwise empty space. The origin of these magnetic fields presents one of cosmology's greatest mysteries. Standard models of cosmic evolution cannot easily explain how magnetic fields of this strength could exist in regions with such low matter density. Creating magnetic fields requires electric currents, which require charged particles, which should be extremely rare in void regions. One possibility involves primordial magnetogenesis, the generation of magnetic fields during the very early universe. If cosmic inflation or other early universe processes created seed magnetic fields, these fields could have been stretched and amplified as the universe expanded, creating the large-scale magnetic networks we observe today. Another explanation suggests that the magnetic fields originated from the first stars and galaxies that formed in these regions billions of years ago. Even though most matter eventually evacuated the voids, The magnetic fields created by early stellar activity could persist indefinitely in the low-density environment. The magnetic fields also influence cosmic ray propagation through voids. High-energy particles produced by supernovae, gamma-ray bursts, and other violent events can be guided and deflected by these fields, creating preferential pathways for cosmic ray transport across vast distances. Advanced computer simulations now include magnetic field evolution when modeling cosmic structure formation. These simulations suggest that magnetic fields play a subtle but important role in shaping void evolution, influencing how gas and dark matter flow through these regions over cosmic time. The study of void magnetic fields represents a new frontier in astronomy, requiring innovative observational techniques and theoretical models. Future gamma-ray telescopes and radio arrays will map these invisible structures with unprecedented detail. Some theoretical physicists speculate that void magnetic fields might provide evidence for exotic physics beyond the standard model. If these fields have unusual properties or unexpected strengths, they could reveal new fundamental forces or particles. The magnetic field discovery proves that cosmic voids are not truly empty, but contain invisible infrastructure that spans the largest scales in the universe. Even in the loneliest regions of space, invisible forces connect distant shores across oceans of darkness. The Boötes Void presents a fundamental challenge to cosmic inflation theory, the leading explanation for how the universe evolved from subatomic scales to its current vast structure, forcing physicists to reconsider the most basic assumptions about cosmic origins. Cosmic inflation theory proposes that during the first fraction of a second after the Big Bang, the universe expanded exponentially, growing from smaller than a proton to roughly the size of a grapefruit in less than 1/trillionth of a trillionth of a trillionth of a second. This violent expansion stretched tiny quantum fluctuations in the primordial universe to cosmic scales, creating the density variations that eventually became galaxies, clusters, and voids. The theory successfully explains many observed features of the universe, including its overall flatness and the patterns visible in the cosmic microwave background radiation. However, standard inflation models predict that the largest possible structures should be limited by the size of the cosmic horizon during inflation. This horizon sets a natural scale for how large coherent structures can become, roughly equivalent to regions that were in causal contact during the inflationary epoch. Calculations based on standard inflation theory suggest that cosmic voids should not exceed approximately 150 million light-years in diameter. The Boötes Void, at 330 million light-years across, more than doubles this theoretical maximum. Even more problematic, the void's nearly perfect spherical symmetry suggests it formed from a coherent underdensity that exceeded the causal horizon during inflation. Creating such large-scale coherence requires physical processes that could operate faster than light, violating the fundamental principles underlying inflation theory. Some cosmologists have proposed modifications to standard inflation that could accommodate supervoids like Boötes. These models invoke multiple inflation fields, phase transitions during inflation, or exotic initial conditions that could create larger, coherent structures. One possibility involves eternal inflation, where different regions of space underwent inflation for different durations. In this scenario, our observable universe might contain patches that inflated longer than others, creating unusually large voids or density fluctuations. Another explanation suggests that the void formed through post-inflationary processes such as phase transitions in dark matter or dark energy that occurred long after the initial inflationary epoch. These later events could have carved out large, empty regions without violating the constraints of standard inflation theory. The problem extends beyond just the Boötes Void. Astronomical surveys have discovered numerous supervoids and superclusters that appear to exceed the scales predicted by standard inflation models. The entire cosmic web structure might be more extreme than inflation theory can easily accommodate. Some theoretical physicists have suggested abandoning inflation altogether in favor of alternative theories such as cyclic cosmology or emergent gravity models. These theories make different predictions about large-scale structure formation and might better explain the existence of extreme cosmic structures. The controversy has motivated new observational programs designed to measure the statistical properties of cosmic voids with unprecedented precision. The European Space Agency's Euclid mission will map millions of voids across cosmic history, providing crucial tests of different inflation models. Advanced computer simulations now explore how various inflation scenarios would produce different patterns of cosmic structure. By comparing these predictions with observations of supervoids like Boötes, cosmologists hope to distinguish between competing theories of cosmic origins. The stakes in this debate extend to fundamental physics. If standard inflation cannot explain the largest structures in the universe, it might indicate gaps in our understanding of quantum gravity, particle physics, or the nature of space-time itself. The Boötes Void stands as a cosmic challenge to our deepest theories about how the universe began and evolved into its current form. The temperature of empty space itself varies throughout the universe, and within cosmic voids like Boötes, the fundamental thermal properties of space-time differ measurably from the cosmic norm, creating regions that are colder than anything achievable in earthly laboratories. Even completely empty space possesses a background temperature due to the cosmic microwave background radiation, the afterglow of the Big Bang that permeates every region of the universe. This radiation currently measures 2.725 degrees Kelvin, just above absolute zero. However, this temperature is not perfectly uniform throughout space. Regions of different matter density create subtle temperature variations through several physical mechanisms that operate on cosmic scales. Within the Boötes Void, the cosmic microwave background radiation appears slightly colder than the universal average. This temperature decrease results from the integrated Sachs-Wolf effect, where photons lose energy as they travel through regions of decreasing gravitational potential. As ancient light passes through increasingly empty regions over billions of years, it gives up energy to the expanding space around it. This energy loss manifests as a temperature decrease that accumulates over cosmic time, making void regions measurably cooler than dense areas. Measurements using the Planck satellite reveal that the cosmic microwave background temperature within large voids can be up to 20 microkelvin colder than the cosmic average. While this difference sounds tiny, it represents a detectable signature of how cosmic structure affects the fundamental thermal properties of space. The temperature difference also affects the quantum vacuum itself. Empty space contains virtual particle pairs that constantly pop into existence and annihilate, contributing to the vacuum energy density. The rate of these quantum fluctuations depends subtly on local gravitational conditions and space-time curvature. Within cosmic voids, where gravitational fields are weaker than average, quantum vacuum fluctuations proceed at slightly different rates than in dense regions. This creates measurable differences in phenomena such as the Casimir effect and spontaneous particle creation rates. The thermal properties of void regions also influence how matter behaves when it does enter these areas. Gas clouds falling into voids experience different cooling and heating rates due to the altered radiation environment and reduced gravitational interactions. These temperature effects have practical consequences for astronomical observations. Telescopes observing through cosmic voids detect subtly different background radiation levels, requiring corrections to measurements of distant objects located beyond void regions. Some theoretical models predict even more extreme temperature variations within the centers of the largest voids. If these models are correct, the most empty regions of space might be cooler than any temperature achieved in laboratory experiments on Earth. The study of void temperatures also relates to fundamental questions about the nature of dark energy. Different dark energy models make different predictions about how empty regions should evolve thermally over cosmic time. Future space-based infrared telescopes will map cosmic temperature variations with unprecedented precision, revealing how the thermal structure of the universe relates to the distribution of matter and dark energy. The temperature measurements also provide tests of general relativity and alternative theories of gravity. Modified gravity theories often make different predictions about how gravitational fields should affect space-time temperature in low-density environments. Advanced laboratory experiments are attempting to recreate void-like conditions on small scales, using sophisticated vacuum chambers to study how quantum effects behave in extremely low-density environments. The discovery that empty space has measurably different temperatures in different cosmic environments reveals that even nothingness itself has structure and properties that vary throughout the universe. In the coldest regions of cosmic voids, space itself reaches temperatures that approach the fundamental limits of how cold anything can become. Light from distant galaxies bends and distorts as it passes through cosmic voids, revealing that even these apparently empty regions contain invisible matter distributed in ways that challenge our understanding of cosmic structure formation. Gravitational lensing occurs when massive objects warp space-time, causing light rays to follow curved paths rather than straight lines. This effect, predicted by Einstein's general relativity, has been observed around galaxy clusters, individual galaxies, and even dark matter concentrations. What surprised astronomers was discovering measurable lensing effects from cosmic voids, regions that should contain too little matter to significantly bend light. Advanced surveys using the Hubble Space Telescope and ground-based observatories have detected systematic distortions in galaxy shapes that indicate the presence of invisible matter within void regions. The lensing signal from voids appears as weak but statistically significant stretching of background galaxy images. Thousands of galaxies located behind voids show coherent shape distortions that can only result from gravitational effects of matter along the line of sight. This invisible matter amounts to roughly 15 to 20% of the cosmic average density, much higher than the few percent suggested by visible galaxy counts within voids. The discrepancy reveals that voids contain substantial amounts of dark matter and possibly diffuse ordinary matter that does not form visible structures. Computer simulations of cosmic structure formation predict exactly this type of residual matter within voids. As overdense regions collapse to form galaxies and clusters, they cannot evacuate void interiors completely. Some dark matter and gas remain distributed throughout the void volume in forms too diffuse to detect directly. The lensing measurements provide the first direct evidence for this predicted residual matter. By measuring the strength of the lensing signal, astronomers can estimate the total mass contained within void regions and map how it is distributed in 3 dimensions. The results reveal that cosmic voids have internal structure invisible to conventional galaxy surveys. Rather than being completely smooth, voids contain networks of dark matter filaments, sheets, and nodes that mirror the cosmic web structure, but at much lower density. Some of the most sensitive lensing studies have detected individual dark matter concentrations within voids, regions massive enough to host galaxies, but apparently lacking the visible matter necessary for star formation. These dark galaxies might represent failed galaxy formation events where cooling processes never triggered star formation. The weak lensing technique also reveals how void structure evolves over cosmic time. By observing voids at different distances, and thus different epochs in cosmic history, astronomers can trace how the residual matter within voids redistributes as the universe expands. Future lensing surveys will map void dark matter with unprecedented detail. The European Space Agency's Euclid mission and the Large Synoptic Survey Telescope will observe millions of background galaxies, providing statistical maps of invisible matter throughout the cosmic web. These observations might reveal whether dark matter has exotic properties that affect its behavior in low-density environments. If dark matter consists of particles that interact weakly with each other, these interactions might be more detectable in void regions where other effects are minimized. The lensing studies also test alternative theories of gravity that propose modifications to general relativity on cosmic scales. These theories make different predictions about how gravitational effects should behave in extremely low-density environments. Perhaps most intriguingly, some lensing measurements suggest that certain void regions contain more invisible matter than standard cosmological models predict. If confirmed, this excess could indicate unknown forms of dark matter or energy that concentrate preferentially in underdense regions. The discovery that cosmic voids lens background light proves that apparent emptiness can be deceiving, and that the universe's invisible components dominate even in its most barren regions. Within the vast emptiness of cosmic voids like Boötes, conditions exist that might allow exotic forms of dark matter to congregate in ways impossible elsewhere in the universe, creating laboratories for discovering new fundamental physics. Most dark matter models assume that dark matter particles interact only through gravity, making them essentially invisible except for their gravitational effects on ordinary matter and light. However, some theoretical models propose that dark matter might have additional properties that become important under specific circumstances. Self-interacting dark matter models suggest that dark matter particles can collide and scatter off each other, though these interactions remain much weaker than those affecting ordinary matter. In dense regions of the universe, such interactions would be overwhelmed by gravitational effects and impossible to detect. But within cosmic voids, where gravitational fields are minimal and matter moves slowly, subtle self-interactions between dark matter particles might become detectable. Computer simulations of self-interacting dark matter predict that these particles would behave differently in void environments, potentially creating observable signatures. Some models predict that interacting dark matter particles would form diffuse clouds or streams within voids, following patterns distinct from the purely gravitational clustering seen elsewhere. These structures might be detectable through their gravitational lensing effects, or their influence on the few galaxies that do exist within voids. Other exotic dark matter theories involve particles that can decay into lighter particles over extremely long timescales. In dense regions of the universe, decay products would be difficult to distinguish from other astrophysical phenomena. Within voids, however, any detected particles or radiation would almost certainly result from dark matter decay. Sterile neutrinos represent one category of exotic dark matter that might concentrate preferentially in void regions. These hypothetical particles would interact even more weakly than ordinary neutrinos, allowing them to stream freely through dense regions but potentially accumulate in cosmic voids over billions of years. Axions, another theoretical dark matter candidate, could exhibit unusual behavior in the weak magnetic fields that permeate void regions. Under specific conditions, axions might convert into photons, creating detectable radiation signatures from otherwise empty regions of space. The search for exotic dark matter in voids motivates several ongoing observational programs. Radio telescopes scan void regions for unexpected emission that might result from dark matter interactions or decay. X-ray and gamma-ray observatories look for high-energy signatures that could indicate exotic particle processes. Some of the most sensitive searches involve studying the kinematics of the few galaxies that exist within voids. If exotic dark matter affects galactic dynamics differently than ordinary dark matter, void galaxies might show unusual rotation patterns or structural properties. The Boötes Void provides an ideal laboratory for these searches because of its extreme emptiness and well-characterized structure. Any unexpected signals detected from this region would be difficult to explain through conventional astrophysical processes. Advanced computer simulations now model how various exotic dark matter candidates would behave within void environments. These simulations make specific predictions about observable signatures that could distinguish between different theoretical models. The upcoming generation of astronomical surveys will provide unprecedented sensitivity for detecting exotic dark matter signatures. The combination of improved instruments and the vast volumes of space contained within cosmic voids creates opportunities for discoveries impossible in dense regions of the universe. If exotic dark matter does exist and concentrate within voids, these discoveries could revolutionize our understanding of fundamental physics and reveal new laws governing the behavior of matter on cosmic scales. The apparent emptiness of cosmic voids might conceal the most exotic forms of matter in the universe, waiting to be discovered by sufficiently sensitive observations. Scattered throughout the Boötes Void, invisible primordial black holes formed in the first moments after the Big Bang might lurk undetected, providing a solution to multiple cosmic mysteries, while remaining hidden from all current observational methods. Primordial black holes differ fundamentally from the stellar black holes formed by collapsing massive stars. Instead of forming from gravitational collapse of existing matter, primordial black holes condense directly from extreme density fluctuations in the very early universe, before the first stars ever existed. These ancient black holes could have masses ranging from microscopic to thousands of times more massive than our Sun. The smallest ones would have evaporated long ago through Hawking radiation. But intermediate mass primordial black holes could survive to the present day. Computer simulations suggest that if primordial black holes formed in significant numbers during the early universe, many would now reside within cosmic voids. The same gravitational processes that evacuated ordinary matter from these regions would have less effect on black holes, which interact primarily through gravity. Unlike stars or galaxies, isolated primordial black holes produce no light and remain effectively invisible unless they actively accrete matter or gravitationally lens background objects. Within the near-perfect vacuum of cosmic voids, these black holes would have virtually no material to consume, making them undetectable by conventional astronomical observations. However, primordial black holes could explain several puzzling aspects of cosmic void structure. The gravitational effects of numerous small black holes distributed throughout void volumes might account for the subtle gravitational lensing signals detected from these apparently empty regions. Some theoretical models suggest that primordial black holes could comprise a significant fraction of dark matter. If this is correct, cosmic voids would contain vast populations of invisible black holes, making these regions far more massive than their apparent emptiness suggests. The detection of gravitational waves by LIGO and other interferometers has renewed interest in primordial black holes as dark matter candidates. Some of the black hole mergers detected by these instruments might involve primordial black holes rather than those formed from stellar collapse. Cosmic voids provide natural laboratories for testing primordial black hole theories. Future gravitational wave detectors will be sensitive enough to detect mergers of intermediate mass black holes throughout the observable universe, including those within void regions. The upcoming Nancy Grace Roman Space Telescope will conduct surveys sensitive to gravitational microlensing events caused by isolated black holes. If primordial black holes populate cosmic voids, they should occasionally pass in front of distant stars, creating brief brightening events detectable by these surveys. Radio astronomy offers another potential detection method. If primordial black holes occasionally capture and disrupt small objects such as asteroids or comets, these events could produce brief radio flashes detectable by next-generation radio telescopes. The study of fast radio bursts, mysterious millisecond duration radio signals from across the universe, might also relate to primordial black holes in voids. Some theoretical models suggest these bursts could result from interactions between primordial black holes and ambient matter in low-density environments. Advanced computer simulations now model how populations of primordial black holes would affect cosmic structure formation over billions of years. These simulations predict subtle but detectable signatures in the distribution and properties of galaxies near void boundaries. The search for primordial black holes in cosmic voids represents one of the most challenging problems in observational astronomy. These objects could revolutionize our understanding of dark matter, early universe physics, and the formation of cosmic structure. If confirmed, primordial black holes in voids would reveal that the most empty regions of space harbor some of the most extreme objects in the universe, invisible gravitational monsters left over from cosmic dawn. The ultimate irony: cosmic deserts might teem with black holes. If intelligent civilizations exist elsewhere in the universe, they might view cosmic voids not as empty wastelands, but as premium real estate, offering unique advantages for interstellar travel, communication, and mega-engineering projects impossible anywhere else. The extreme emptiness of cosmic voids eliminates most of the hazards that make interstellar travel dangerous in dense regions of the universe. Cosmic radiation levels drop to minimal levels when distant from active galaxies and star-forming regions. Asteroid impacts, stellar collisions, and gravitational perturbations from massive objects become virtually non-existent. For a civilization attempting to travel between galaxies separated by hundreds of millions of light-years, voids provide the safest possible routes. Spacecraft could maintain straight-line trajectories for enormous distances without navigational corrections or course adjustments needed to avoid stellar hazards. The weak gravitational fields within voids offer unique opportunities for exotic propulsion systems that require minimal interference from external forces. Theoretical concepts such as warp drives or space-time manipulation technologies might function more efficiently in regions where background gravitational noise reaches minimum levels. Advanced civilizations might also exploit voids for massive engineering projects spanning multiple galaxy-sized volumes. The construction of Dyson spheres around individual stars represents child's play compared to megastructures that could span entire void regions, potentially enclosing volumes containing billions of potential stellar systems. Communication advantages within voids could prove equally valuable. Radio signals, laser communications, and exotic faster-than-light communication schemes would face minimal interference or absorption when traveling through near-perfect vacuum across cosmic distances. The temperature properties of void regions create natural refrigeration on scales impossible to achieve artificially. Advanced computers or other technologies requiring extremely low operating temperatures could function more efficiently within the coldest regions of cosmic voids. Resource extraction presents unique opportunities within voids. While matter density remains low, the absolute volume of space is so enormous that even sparse resources become abundant when harvested across sufficient distances. Advanced civilizations might develop technologies to extract and concentrate the diffuse matter pervading void interiors. The few galaxies that exist within voids could serve as rest stops or refueling stations for intergalactic travelers. These isolated galaxies would offer gravitational anchor points and stellar resources spaced at manageable intervals across otherwise empty expanses. Some theoretical scenarios suggest that sufficiently advanced civilizations might artificially create or enlarge cosmic voids to serve their purposes. The energy requirements would be staggering by current human standards, but might be feasible for civilizations capable of harnessing the energy output of entire galaxies. From a military or defensive perspective, voids offer ultimate isolation from potential threats. A civilization that relocates to void regions would be virtually impossible to find or attack, protected by distances so vast that even light-speed weapons would take hundreds of millions of years to reach their targets. The search for extraterrestrial intelligence increasingly focuses on detecting mega-engineering signatures that might be visible across cosmic distances. Artificial structures within cosmic voids would stand out dramatically against the natural background, making them potentially easier to detect than similar constructions in crowded galactic environments. Future astronomical surveys designed to map cosmic structure might inadvertently discover evidence of void-based civilizations through unusual infrared emissions, geometric patterns in matter distribution, or other signatures of large-scale engineering projects. The concept of void civilizations also relates to solutions for the Fermi paradox, the apparent contradiction between high probability estimates for extraterrestrial intelligence and the lack of observed evidence. Perhaps advanced civilizations routinely migrate to void regions, explaining their absence from dense galactic neighborhoods. If such civilizations exist, cosmic voids might represent the ultimate frontier of cosmic development, where intelligence and technology operate on scales that dwarf anything conceivable within individual galaxies. The loneliest regions of space might actually be the busiest. Imagine discovering that Earth and our entire local group of galaxies were slowly falling into a cosmic void larger than the Boötes Void, and that this process would fundamentally alter the fate of every star, planet, and living being in our cosmic neighborhood. The scenario begins subtly, with astronomical observations revealing systematic motions of nearby galaxies toward a region of space that appears increasingly empty as telescopes probe deeper. Initial measurements suggest the motion results from gravitational attraction toward a massive but invisible structure beyond current observational limits. As decades pass and observations improve, the true horror becomes clear. We are falling toward the edge of a supervoid, so large, it makes the Boötes Void seem small by comparison. The gravitational field of surrounding galaxy superclusters is pulling our local group inexorably toward this cosmic abyss. The fall would take billions of years to complete, but its effects would become noticeable much sooner. As our local group approaches the void boundary, tidal forces from nearby massive structures would begin disrupting the orbital dynamics of galaxies within our cosmic neighborhood. The Milky Way's collision with Andromeda, predicted to occur in approximately 4 billion years, might be accelerated or altered as both galaxies experience differential gravitational forces during their approach to the void. Instead of a relatively gentle merger, the encounter might become a violent disruption. Once inside the void, our cosmic environment would transform dramatically. The night sky would gradually darken as more distant galaxies redshift beyond visible wavelengths due to accelerated expansion within the void interior. Future civilizations would observe a universe that appears increasingly empty and isolated. The cosmic microwave background radiation would appear cooler and more uniform, erasing much of the information about cosmic structure and evolution that current astronomers use to understand the universe's history. Evidence for the Big Bang might become much more difficult to detect and interpret. Dark energy effects would dominate cosmic evolution within the void, causing space to expand at rates exceeding the cosmic average. This enhanced expansion would eventually overcome the gravitational binding of galaxy clusters, then individual galaxies, and ultimately stellar systems. The few other galaxies sharing our void would become increasingly isolated as expansion carries them beyond the cosmic horizon. Communication and travel between galactic civilizations would become impossible as distances grow faster than light can traverse them. Star formation rates would decline as the void environment offers less raw material for creating new stellar systems. Existing stars would exhaust their nuclear fuel without replacement, leading to a cosmic environment dominated by stellar remnants, white dwarfs, neutron stars, and black holes. The ultimate fate involves thermal death on cosmic scales. As expansion continues accelerating, individual atoms would be pulled apart by dark energy effects, creating a universe consisting entirely of isolated elementary particles spreading through ever-expanding space. However, this nightmare scenario assumes our local group genuinely approaches a massive supervoid. Current evidence suggests we might already reside within a large void structure, but the ultimate consequences remain uncertain, depending on the void's precise properties and evolution. Advanced computer simulations model how cosmic structure evolves within different void environments, providing insights into possible futures for void-dwelling civilizations. These simulations suggest that while void environments pose unique challenges, they might also offer opportunities for exotic physics and engineering projects. The study of void dynamics helps astronomers understand whether our cosmic neighborhood faces such a fate and provides early warning signs that would become detectable long before any catastrophic effects begin. For now, falling into a supervoid remains a theoretical possibility rather than an immediate threat, but it illustrates how cosmic structure evolution could dramatically alter the future of intelligence in the universe. The next generation of astronomical instruments will reveal cosmic voids so enormous they will make the Boötes Void appear small, pushing the boundaries of what we thought possible in cosmic structure and challenging our fundamental understanding of universal architecture. Current void surveys have mapped only a tiny fraction of the observable universe. The Sloan Digital Sky Survey, TWAD-F Galaxy Redshift Survey, and other major projects have catalogued millions of galaxies, but these surveys cover less than 10% of the sky and probe to relatively modest cosmic distances. The upcoming Euclid space mission will survey 15,000 square degrees of sky, mapping the three-dimensional positions of over 1 billion galaxies across cosmic time. This unprecedented survey will reveal void structures throughout a volume roughly 1,000 times larger than previous studies. Computer predictions based on current cosmological models suggest that voids larger than the Boötes Void should exist within the observable universe, but remain undiscovered due to observational limitations. Statistical calculations indicate that voids exceeding 500 million light-years in diameter likely exist, waiting to be found by sufficiently comprehensive surveys. The Vera Rubin Observatory, beginning operations in the mid-2020s, will photograph the entire visible sky every 3 nights for 10 years, creating the most complete map of cosmic structure ever attempted. This survey will detect galaxies too faint for previous studies and reveal the full extent of void networks throughout the local universe. Advanced machine learning algorithms will analyze these enormous datasets, identifying void structures through subtle statistical patterns invisible to traditional analysis methods. These AI systems might discover void types or characteristics that human astronomers never anticipated. The combination of improved survey depth and sky coverage will likely reveal supervoids with properties that challenge current theoretical models. Voids approaching 1 billion light-years in diameter might exist in the deepest regions of space, created by physical processes we do not yet understand. Radio astronomy offers complementary approaches to void discovery. The Square Kilometre Array, currently under construction, will map hydrogen gas throughout cosmic voids with unprecedented sensitivity. These observations might reveal previously unknown structure within apparently empty regions. Gravitational wave detectors represent another frontier for void studies. As these instruments become more sensitive, they will detect black hole mergers and other events occurring within cosmic voids, providing new ways to probe the matter, content, and evolution of these regions. The study of cosmic voids will also benefit from advances in computational cosmology. Exascale supercomputers will simulate cosmic structure formation with resolution and scope impossible today, predicting where the largest voids should exist and what properties they should have. These simulations might reveal that our current understanding of void formation is incomplete. If dark matter has exotic properties, or if dark energy behaves differently than assumed, the universe might contain void structures far more extreme than standard models predict. Multi-messenger astronomy, combining observations across the electromagnetic spectrum with gravitational waves and neutrino detections, will provide comprehensive views of void environments. These combined observations might reveal hidden components of cosmic structure invisible to any single type of measurement. The discovery of larger voids will have profound implications for cosmology and fundamental physics. If voids significantly larger than current models allow are found, it could indicate problems with our understanding of cosmic inflation, dark matter properties, or the large-scale homogeneity of the universe. Future void discoveries might also reveal connections between cosmic structure and exotic physics, such as extra dimensions, modified gravity theories, or interactions between our universe and parallel cosmic domains. The exploration of cosmic voids represents one of the last frontiers in mapping the universe's architecture. As our observational capabilities expand, we can expect to discover void structures that surpass our current imagination and challenge our deepest assumptions about cosmic evolution. The largest holes in space remain to be found. The Boötes Void provides a terrifying preview of our universe's ultimate destiny, revealing how dark energy will eventually transform all of space into lonely, cold expanses where isolated remnants drift through ever-expanding darkness. Current observations confirm that cosmic expansion is accelerating due to dark energy, the mysterious force that comprises roughly 68% of the universe's total energy density. This acceleration means that distant galaxies are moving away from us at increasing speeds, and this trend will continue indefinitely into the future. Computer models of cosmic evolution reveal that as dark energy continues driving accelerated expansion, the universe will undergo several dramatic transitions. Cosmic voids like Boötes represent snapshots of what most of the universe will eventually become. Vast, empty regions where matter exists only in isolated pockets, separated by enormous distances. Within approximately 100 billion years, accelerated expansion will carry distant galaxies beyond our cosmic horizon, making them permanently invisible to any observer in our local group. The observable universe will shrink dramatically as more and more galaxies disappear behind the expanding cosmic horizon. The Boötes Void shows us what this future looks like. Galaxies within the void are already so isolated that observers on planets in these systems can see only a handful of neighboring galaxies in their night sky. As expansion continues, even these few neighbors will eventually disappear. But the cosmic isolation process will not stop with galaxies. As dark energy continues to dominate cosmic evolution, it will overcome weaker and weaker gravitational bindings. Galaxy clusters will dissolve as expansion carries their member galaxies apart. Individual galaxies will lose their outer regions as dark energy overcomes the gravitational binding of stars to galactic centers. Eventually, dark energy might become so dominant that it overcomes the gravitational binding of individual stellar systems. Planets would be pulled away from their parent stars, and stars themselves might be torn apart if dark energy's influence continues growing stronger over time. The study of void dynamics helps astronomers understand this process because voids represent regions where dark energy already dominates over gravitational attraction. Within the Boötes Void, dark energy drives expansion at rates exceeding the cosmic average, providing laboratories for studying how matter behaves when gravitational binding becomes negligible. Temperature measurements within voids reveal the thermal future of our expanding universe. As space expands and matter becomes increasingly dilute, the average temperature of the universe will continue dropping toward absolute zero. Void regions already approach this ultimate cold future. The magnetic fields discovered within cosmic voids might represent some of the most persistent structures in the far future universe. While matter and radiation disperse due to cosmic expansion, magnetic field lines can stretch across enormous distances and persist for extremely long periods. Some theoretical models suggest that the universe's expansion might eventually reverse if dark energy has exotic properties that change over cosmic time. However, observations of cosmic voids provide no evidence for such behavior, instead showing that dark energy effects become more pronounced in the most underdense regions. The ultimate fate implied by void studies involves a universe consisting mostly of empty space, punctuated by isolated black holes, white dwarf stars, and elementary particles. Even these remnants will eventually decay through quantum processes, leaving behind only photons and leptons in an ever-expanding, ever-cooling cosmos. This scenario, known as the heat death of the universe, represents the most likely outcome based on current understanding of dark energy and cosmic evolution. Cosmic voids provide direct observational evidence that this process has already begun in the most underdense regions of space. However, the study of voids also reveals that the universe might surprise us. If these regions contain exotic matter, hidden structures, or unexpected physical processes, the cosmic future might differ from current predictions. The Boötes Void stands as a monument to the ultimate victory of dark energy over gravity, expansion over attraction, isolation over connection. It shows us the destiny that awaits all cosmic structure in the distant future when the universe completes its journey from the dense, hot conditions of the Big Bang to the cold, empty expanses of eternal expansion. In the end, all will become void,